Hello friends, today we are going to talk about the last part of the lecture entitled Engineering Disordered Fibrous Materials via Theory of Fiber-to-Fiber Contacts. So that this part of the lecture is focused on the application of theory of fiber-to-fiber contacts. As we have learned earlier, the theory of fiber-to-fiber contacts can be a useful technique to compute the fiber-to-fiber contacts in random or anisotropic fibrous assemblies. And in this part of the lecture, we are going to talk about how we can apply the theory of fiber-to-fiber contacts in predicting certain mechanical properties. We have shown this slide in the last part of the lecture. As you can see here, we have understood the method to calculate number of fiber-to-fiber contacts in a mesodomain based upon the total number of fiber-to-fiber contacts in a defined volume. A mesodomain is defined as a volume which has a unit cross-sectional area, as you can see in this figure, and it has thickness of mean distance between the fiber-to-fiber contacts projected on a thickness or projected on a certain plane. So, you can calculate the number of fiber-to-fiber contacts in mesodomain with a volume dV in terms of fiber volume fraction, fiber diameter, and the directional parameter, which indicates the projection of fibers being aligned in certain direction projected on a certain plane. So, Kj or the directional parameter is a function of orientation distributions and the alignment of fibers. And for a 3-dimensional random fibrous assembly, we have computed this value, which comes out to be half. So, we are going to make use of number of fiber-to-fiber contacts in a mesodomain for predicting certain mechanical properties. So, today we are going to talk about a very interesting application where we can make use of theory of fiber-to-fiber contacts. One such application is absorptive glass mat separator. What is it and where it is being used? This kind of material is used in valve regulated lead acid battery, which is common variant of lead acid battery, which are immensely used in day to day purposes, for example, in inverter batteries, automobile batteries. And VRLA batteries are classified into two types. One of them is a gel type and the other one is absorptive glass mat type. So, I am going to give you an example where the theory of fiber-to-fiber contact can be a useful approach to predict certain mechanical properties of these absorptive glass mat separators. But before that, we should understand what are the main constituents of VRLA battery. In general, the key components of VRLA battery consist of a positive plate, negative plate, electrolyte, and a separator which is sandwiched between these plates to prevent a short circuit between the positive and negative plates. So, you have two plates, for example, this can be a positive plate, the other one can be a negative plate. So, in between we have this AGM separator. Okay. So, the main function of AGM separator is basically to separate these two electrodes so that you can prevent the short circuit. An AGM separator is composed of very fine glass fibers, for example, in the range of 0.25 microns to 4 microns in diameter, and these glass mats are produced using a wet laying process. So, the first function of this AGM separator is to prevent a short circuit between the positive and negative plates. The second function of this AGM separator is to establish an oxygen recombination cycle. What an oxygen recombination cycle is? The VRLA battery operates on the principle that during charging, the oxygen evolved at the positive plate reacts with the hydrogen generated at the negative plate to produce water, provided that the gas is channelized through the separator in a controlled manner. So, the oxygen is being released from the positive plate during charging of the battery, and then it comes in contact with the hydrogen which is released at the negative plate to produce water. As you all know that we always need to fill the batteries quite often with water, and this is one of the reasons that water loss is actually happening within a VRLA battery over the period of time. So, in order to reduce the loss of water, a defined amount of oxygen has to pass through the AgM separator, which is immobilized in a sulfuric acid solution, or we also call it as electrolyte. So, our AgM separator is partially saturated with electrolyte. So, the oxygen has to pass through the partially saturated AgM separator to reach to the negative side of the plate to form water. So, the pore size distribution of these separators is significantly important, which are dependent upon the number of fiber to fiber contacts as we have discussed earlier. But one of the most important functions of the AgM separators is to retain the sulfuric acid or electrolyte reliably, because what happens is, if a large amount of oxygen passes from the positive plate to the negative plate, then and the amount of hydrogen is not sufficient to form water, then there will be large amount of gas which would be produced in the battery, and there is a possibility that a thermal runaway issue can occur in the battery, which can even lead to the explosion of the battery. But the most important function of the AgM separator is to maintain its compression resistance and recovery characteristics. Why compression resistance and recovery are important? As you can see, during discharging of the battery, the plates come closer to each other and they compress the AgM separator, as you can see. So, compression is happening during the discharge of the battery, and during the charging the material expands and the recovery of the material is taking place. That means, during the charge and discharge modes of the battery, the compression and recovery of AgM separator is taking place. During the mode of compression, all the above mentioned characteristics of AgM separators are significantly influenced. For example, the pore size, which is also being affected by the mode of compression force. Similarly, the wicking characteristics, because the sulfuric acid has to move in an AgM separator, or the distribution of sulfuric acid is significantly dependent upon the wicking characteristics of these glass fiber mats. So, during compression, the sulfuric acid would be pushed out of this AgM separator, and apparently there will be a loss of electrolyte solution, and in that case obviously more oxygen would transport from the positive plate to the negative plate, and as we discussed earlier, then there is a possibility of thermal runaway issue that can actually take place. So, compression and recovery characteristics are significantly important for AgM separators. Specifically, the other component of compression is recovery, because if the recovery is not complete or the full recovery of the AgM separator does not happen, in that case there is a loss of contact between the plates and the AgM separator. So, AgM separator would lose its thickness over the period of time, and it would lose the contact during the compression and recovery of these materials, or during the charge discharge modes of the battery. So, then there would be a good chance that a short circuit may happen. So, AgM separator would not be able to fulfill these functions if it is not able to maintain its compression resistance and recovery characteristics. In this regard, We can discuss the structure analysis of AGM separators first, and then you will be able to see how we have made use of number of fiber to fiber contacts formed in a meso domain to predict certain properties of these materials. So, in the macro scale you have a battery, as you can see there are certain positive and negative plates. In between you have U shape AGM separators, and now we know what are the functions of these AGM separators. So, this is a macro scale. So, all the dimensions are in, let us say, in centimeters. Then we look at the specific region of AGM separator, as you can see in between, which we call it as mesoscale, and this mesoscale, as we discussed earlier, is defined by two section planes of unit cross sectional area. The thickness of this plane is defined by Bj bar. Now we have moved to the micro scale, where you have a micro element of fiber which is projected on z direction in this case, and the thickness of this meso domain is dictated by the Bj bar, which is a mean distance between the fiber to fiber contacts projected on this z direction or on the thickness direction. So, we can relate the micro scale with the mesoscale, and then mesoscale can be a part of macro scale to understand the characteristics of AGM separators. So, now we are going to look at the deformation mechanism of AGM separator specifically under compression load. So, let us say the compressive stress P be applied to the AGM separator. This compressive stress would be translated to the fibers, and let us look at the cross section of these fibers. In fact, we have just shown couple of fibers here, and Cj be the average force acting on a fiber to fiber contact, and this average force can be translated into the normal force and the parallel force, which is shown by Cjp, and the normal force is denoted by Cjn. So, the action of these two forces deform the fiber element in this case. So, Cjn would actually bend the fibers and Cjp would stretch the fibers. Since the stretching phenomena is least expected in glass fibers, because the bending stiffness of the fiber is lower than the tensile stiffness. So, apparently the chances of bending during compression load would be much higher. So, let us assume the bending deformation of the fiber is taking place within the structure. So, now there are two possibilities again. One of the possibilities is that the fiber can bend, which is shown here, and or the fiber can slip, but that depends upon certain critical polar angle, and we already know what a polar angle is, which is the out of plane orientation angle of the fibers. So, when you apply a load Cj on the fibers, there is a chance that the fiber can either bend or the fiber can slip, as shown in the lower figure, but that depends upon the critical angle, which is shown here, and the critical polar angle depends upon the frictional properties, that means the coefficient of friction, which is denoted here by mu, and the internal friction, which is shown here by means of Wf naught, which is present in the system, B bar, which is the mean distance between the fiber to fiber contacts, and we already know Cj is already involved in compressing the fiber element. So, in this case we are able to classify either the bending of the fiber segment or the slippage of the fiber segment depending upon the critical polar angle. So, once we know the fraction of slipping contacts, we can actually calculate how much is the load being transferred to the slipping contacts and to the non-slipping contacts. So, compressive stress is distributed in the slipping component and in the non-slipping component. So, slipping component involves the fraction of the slipping contact, which is Fs, and NdV is an important component. That means how many fiber to fiber contacts are taking place in a defined meso domain. As we have already mentioned in the last lecture, NdV is representing the number of fiber to fiber contacts in meso domain of volume dV, and this meso domain is just like a repeating unit within the system. So, now we know how much is the load being transferred in the slipping and the non-slipping component. So, now we just need to calculate the fraction of proportion of slippage contacts, which is shown by this lower equation by means of the fiber orientation distributions and on the basis of critical polar angle, which we have shown in the last slide. So, this is how we can calculate Fs. So, we can calculate the how much is the load being transferred into the system on the basis of the meso domain or on the basis of the NdV. And similarly, we can calculate how much is the force being transferred to the slipping contact by using this equation, where Csj is the proportion of force that is being transferred to the slippage contacts on the basis of withdrawal forces, mean distance between the contacts, the critical polar angle and coefficient of friction. And once we know the values of Csj and Fs and NdV, we can calculate how much is the load being transferred to the non-slipping contacts by rearranging this equation. So, you can see the non-slipping contact here is the component of fibers that are going to bend between the two successive fiber to fiber contacts. So, this is the average load which is being transferred to the fibers in the non-slipping contact, which can lead to the bending deformation of fibers within the meso domain NdV. So, now we can also make use of meso domain for the recovery behavior. And how do we do that? So, during the recovery stage, the compression load is released gradually in succession of reduction in the magnitude of Cj, which is the average force applied to a defined fiber to fiber contact in the meso domain of volume dV. So, in such a case, the behavior of slipping contacts would differ from the compression state. The stored bending energy in the fibers is the primary cause of recovery of AGM. So, the recovery behavior of AGM separator would depend upon the elastic behavior of the fibers that were actually bent, and the energy losses would be considered for the fiber slippage. So, we can actually calculate the recovery force, which is dependent upon the fiber bending component. So, how many proportion of fibers were compressed and how much load is being taken by these fibers, and how much is the slippage which has taken place. On the basis of simple calculations, we can calculate the cumulative pressure losses during the successive iteration using this last equation. So, if you see here, the Pri is the remnant stress at the ith level of iteration. That depends how much is the loss between the bending stresses, which is shown here by Pb, and the losses which has occurred due to the slippage component and also due to the withdrawal forces, which is internal friction of the fiber itself. So, we can actually calculate the remnant pressure or the remnant stresses that can lead to the recovery characteristics of these AGM separators. So, number of fiber to fiber contacts in meso domain can be a useful technique in computing the compression and recovery behavior of AGM separators. Next, we look at an example where we try to develop a tensile model using theory of fiber to fiber contacts by a simple technique. Here we assumed that there is a single fiber connected by means of two fiber to fiber contacts. So, there is a fiber being connected by two successive contacts, and again we make use of meso domain, we try to calculate the total stress, which is denoted here by sigma, and here we try to calculate the tensile characteristics, let us say for a thermally bonded non-woven material, where all the fibers are completely fused with each other, and the fiber to fiber contact is presumably a stronger contact in case of thermally bonded non-woven. So, in this case the total stress, which is shown here by sigma, and then Ff is the force which is experienced by the fiber, and since we assume that there is a defined test direction which is shown here by means of alpha. So, in this in plane tensile loading, there is a projection of fiber force on the defined test direction. So, Ff cos beta represents the projection of the force experienced by the fiber on the defined test direction. So, beta, if you see here, is psi minus alpha, which is psi is the alignment of the fiber and alpha is the defined test direction. So, Ff beta cos beta is the projection of the fiber on the test direction where we are testing the material, and then we have chi beta, which represents the orientation distribution of the fibers, and then we multiply here with the help of NdV again. So, in this case again you will see that we have to consider a mesodomain, how much is the load being transferred to the fibers and in what direction, and if this is the repeating unit, then we can actually calculate the total stresses experienced by the fibers in the whole fabric, because NdV again represents the number of fiber to fiber contacts in the mesodomain dV. Since Bj bar is there, you will see when you resolve this or when you put the value of NdV, again Kj will come into picture, which we have seen it earlier, and this is a expression of Kj for a 2D material. So, we consider the whole analysis 2-dimensional in nature. So, in this way we are able to develop the tensile model on the basis of fiber to fiber contacts in mesodomain. Similarly, one can also calculate the shear model. So, let us say there is a disordered fiber network and in plane shear has to be derived. So, let us say there are two forces acting on the macro scale or on the fabric itself. So, accordingly there would be a shear force acting on the fiber to fiber contact at the micro scale. So, we can redefine our critical orientation angle in terms of in plane orientation angle, as you can see, which is denoted by psi c. So, when the shear load is being applied to the system, then again we can presume that either the bending of the fibers between the two contacts can take place or the fiber slippage can take place, depending upon the value obtained for critical orientation angle, but this one is the in plane orientation angle. So, psi c is the critical in plane orientation angle which dictates whether the fiber bending or fiber slippage would occur in the system. Again, this is force balance equation which is shown here by making use of the average force which is acting on the fiber to fiber contact Cj or Ck, depending upon the coefficient of friction between the fibers, withdrawal forces and the mean distance between the contacts. So, one can easily calculate critical in plane orientation angle for these fibers. So, again similar to the compression model, we can say that shear stress can be transferred to the slipping and non-slipping contacts, like we have shown it earlier for the compression model. But here the fraction of slippage contacts would depend upon the critical in plane orientation angle of these fibers rather than out of plane orientation angle which was considered for compression model. So, in this way again we can see that we have made use of NdV again. So, mesodomain can be a useful method or can be a useful approach to compute the number of fiber to fiber contacts in a defined fibrous assembly or fibrous material, and we can predict certain properties, certain mechanical properties. In a similar fashion, one can also calculate the geometrical properties. For example, the pore size distribution. We have calculated in the past, depending upon the number of fiber to fiber contacts in mesodomain dV, we can calculate how many contacts are taking place, and on the basis of those contacts one can define the polygonal geometry formed by means of fibers, and one can calculate the pore size distribution for such materials. So, there are certain research challenges in the theory of fiber to fiber contacts as well, although the predictive modeling is certainly very useful using the mesodomain technique, but one has to remember the challenges which are associated with this kind of research work. One of the first challenges that you would experience, that the disordered fiber networks can be highly heterogeneous, non-uniform and anisotropic in nature. What we mean by heterogeneous, there can be local variations, for example, in mass per unit area, in thickness, fiber volume fractions. Such local variations have not been considered in the theory of fiber to fiber contacts. However, such parameters can be considered by making use of statistical analysis such as standard deviation, coefficient of variation for these structural parameters. So, the material can be highly heterogeneous, non-uniform. For example, these disordered materials are not uniformly distributed, which means that at certain regions the fibers can be highly anisotropic in nature. So, in certain disordered fiber networks, you may observe that locally the structure is highly anisotropic, in certain region it is not that anisotropic, but such characteristics have not been considered in this theory of fiber to fiber contacts. Then we have assumed that there is an affine deformation of fibers that take place in the fiber network. What we mean by affine deformation? An affine deformation allows the macroscopic deformation applied on a body to translate uniformly to the microscopic level. For example, in a tensile mode of deformation, we presumed that there exists a relationship between the fiber and fabric strains, which is purely analytical in nature, but this may not be the case every time. So, this means we presume that the average load which is acting on the fiber to fiber contact is same throughout the structure, but it may not be the case for highly disordered fibrous materials. Then it is also quite complex to determine certain structural parameters, for example, fiber volume fractions, out of plane orientation distributions. One can make use of X-ray microcomputed tomography, but still the sample size is quite small during the testing. So, there are chances that you may not have the sample which represents the whole population. So, this is another challenge for further work, that one needs to characterize the input structural parameters, let us say fiber volume fractions and orientation distributions, in a more accurate manner. Then last but not least, the other challenge is pruning the number and type of contacts in the network. So far we presumed that all the fiber to fiber contacts behave in the same manner and all are absolutely same type, but it may not be the case. For example, in a thermally bonded nonwoven, it may happen that certain fibers are fused in nature, but certain fibers have not been fused and there is a frictional fiber to fiber contact which is existing in the structure. So, it is a combination of both the frictional contacts and fused fiber contacts. So, the pruning the number and type of contacts is also a challenge to include in the theory of fiber to fiber contacts. Nevertheless, in this series of lectures, we learned about the importance of theory of fiber to fiber contacts. We know now why they are important, what is the application of these theory of fiber to fiber contacts, how they can be useful for a defined application. We also learnt about the basic principles of stereology and geometrical probability. We can calculate the number of fiber to fiber contacts and the mean distance between them specifically for random and anisotropic materials. So, using Van Wyck's work for random fibrous assembly, we are able to calculate the number of fiber to fiber contacts. Using Komori and Makishima's work, we are able to calculate the number of fiber to fiber contacts and mean distance between the contacts for anisotropic materials. And we also know how theory of fiber to fiber contacts can be applied specifically in predicting certain mechanical properties of these disordered fibrous materials. With this, thank you very much.